So in that next problem, a ring of mass 0.3 kg and radius 0.1 meter. So we are taking that circular ring. So in this circular ring, its mass is the 0.3 kg and after that radius is 0.1 meter, 0.1 meter. And here and a solid cylinder of a mass 0.4 kg and of the same radius. So solid cylinder is here. In this case, it is the mass is the 0.4 kg and again the radius is the same, it is a 0.1 meter. Now here it is a solid cylinder of a mass 0.4 kg and again 0.1 meter is the same radius, and here the same Ke that they are given released simultaneously on a flat horizontal surface such that they begin to roll as soon as released towards a wall with it at the same distance from the ring and the cylinder. Suppose if you are considering this the wall and again that is a circular ring is given and again thereafter it is a solid cylinder is also given, solid cylinder like this, and both are rotated, both are having the same kinetic energy. On reaching this wall, now the question is, on reaching this wall, they begin to roll as soon as released towards a wall which is at the same distance from the ring and the cylinder. The rolling friction is neglected in both cases. Then which will reach the wall first? Then which will reach that wall first? So in this case, rolling friction is neglected. Its meaning is there is no any opposing force. So when there is no any opposing force, definitely with whatever that kinetic energy that you have given here, on reaching this wall also they possess the same kinetic energy. They possess the same kinetic energy. So that's why they possess the same kinetic energy means, so first of all we are taking the ring. So in this ring, its value is E is equal to 1 by 2 mv square of 1 plus k square by r square. And here the kinetic energy for those two bodies and here the kinetic energy on this reaching this wall, and both will be same because there is no any resistance force to oppose the motion of that rolling bodies. Now here E is equal to half mv square of 1 plus k square by r square, and for that ring already you know half mv square is given and that mass is given 0.3. So it is 0.3 is there, and v square is here like this, and thereafter 1 plus k square by r square, 1 plus that k square by r square in case of the ring is it is nothing but 1. Just now we got it, it is 1. So it will be 0.3 v square, that's only 0.3 v square. So it is 0.3, 2 is here, that will be cancelled, 0.3 v square. So now here it is taken the first equation. Here it is taken that first equation. Next, we are coming to this solid cylinder. In case of a solid cylinder, and here it is, you are given E is equal to, because both are having the same energy. Even on reaching this wall also, they will have the same kinetic energy. So that's why E is equal to half mv square is taken, half mv square, and after that 1 plus k square by r square. In a solid cylinder, it is nothing but, in a solid cylinder, it is nothing but 1 by 2, just like it is a disc. So that's why it is a 1 by 2. And here it is half, and m is given 0.4, and it is v square is here, and here it is a 0.4 v square, and it is the k square by r square is equal to 1 by 2. So overall it becomes a 3 by 2. 3 by 2 is here like this. Now this is a E is equal to 0.1 is here, and that is multiplying this 3, 0.3 v square is here. And this is for that ring, and this is for the solid cylinder. This is for the solid cylinder, this second equation. And already you know LHS are same. That's why from 1 and 2, what you can equate, that is RHS. So it is 0.3 v r square, and again the 0.3 v cylinder square is here. Its meaning is Vr is equal to v cylinder. Its meaning is their final velocities are same. On reaching the wall, their final velocities are same. So because of that reason, they reach the wall simultaneously. So there is no question of reaching the first. So that's why to anybody. So that's why it is a rolling ring, and again the cylinder, they reach the wall simultaneously. So this problem is also over. Now we are coming to this next problem. A uniform solid sphere of a mass 1 kg and radius 0.2 meters makes 4 revolutions per second about its diameter. How much torque is required to increase its angular momentum? So how much torque is required to increase its angular momentum about this axis by 10% in 20 seconds? By 10% in 20 seconds is slightly different problem. So in this case what we are taking, that is tau is equal to, so here a uniform solid sphere of a mass 1 kg and radius 0.2 meters. Mass is given 1 kg and again that radius is given, it is 0.2 meters and it is n is equal to 4 revolutions per second. So 4 revolutions per second is given, that is a frequency, and thereafter about its diameter. And here how much torque is required to increase its angular momentum? So that is delta L, that is 10%. What you are given delta L, you are given it is 10 by 100. 10% is given delta L by L. So now it is 10% is given, and thereafter in 20 seconds. So that time is also given, it is 20 seconds like this. Mass is 1 kg. And it is 0.2 meters and 4 revolutions per second, delta L, that is you are given 10% and a fractional how much torque is required to increase its angular momentum. It is a fractional increase of that angular momentum is 10%, percentage increase in that angular momentum is 10%, and thereafter t is equal to 20 seconds. How much torque is required? First we have to frame one formula. Torque is equal to I alpha is here. Torque is equal to I alpha, and here that is already we know that is L is equal to I omega. L is equal to I omega. In place of the I, L by omega to be taken, and alpha is equal to omega by t. Alpha is equal to omega by t, and it is nothing but L by t. Torque is equal to L by t. And when it is taken a delta, torque is equal to delta L by delta t. This is the formula. This is the formula. Ultimately we derived this formula once again. So torque is equal to I alpha. I is equal to L by omega. Alpha is equal to omega by t. After cancelling it becomes L by t. Delta torque is equal to delta L by delta t. That is the first equation. Now we have to find it, that delta L separately. How it is? It is the L is equal to I omega is here, and for that solid sphere, that too about its diametrical axis, and that's why it is 2 by 5 mr square is here. 2 by 5 mr square, that is to be taken, and omega is equal to 2 pi n, that you are given. Omega is equal to 2 pi n. In this case delta L is equal to 10 by 100, because you are already mentioned its value is that 10 by 100 of that original initial value. So that's why delta L is equal to 10 by 100 of mr square. So 2 by 5 mr square of 2 pi n is here like this. 2 pi n. Once again I tell you. So first of all, this is the formula. Torque delta tau is equal to delta L by delta t. Here delta t, there is no problem regarding this delta t. Already you are mentioned that value, it is you are given, it is 20 seconds. The problem is with this delta L only, and for that L is equal to I omega. I is equal to 2 by 5 mr square. Omega is the 2 pi n, and delta L is equal to, you are given that problem, it is a 10%. To increase the angular momentum 10%. So that's why it is given 10 by 100 and 2 by 5 mr square, 2 pi n is there, and it is 0.1. and thereafter it is 0.4, and again m is taken, that m is given that 1 kg, and r is given 0.2, so it becomes 0.04, and thereafter it is 2 pi n. 2 pi n is given 4 revolutions per second, so that's why 4 is also there. Now after solving that becomes, it is 4, and again the 4, 16 into 8, that becomes 128. So 128 is here. Once again I tell you, 4, and again the 4, 16 into 8, that is 128. Now point here, and the 2 and 4, so that's why 0.0128. 0.0128 and ultimately that pi is also there. So this is the value of delta L. This is the value of delta L. Delta L is equal to 0.0128 pi. And now you have to apply these values here. That is, the delta torque is equal to from 1 it is a delta torque is equal to this much 0.0128 pi, that is a 3.14 and delta t already you are given it is a 20 seconds. So 20 seconds is there. Then you can get that answer. It is 0.002. That's all. That is torque required to increase that angular momentum by 10%. A carpet of mass m. This is slightly difficult because this problem is based on that conservation of energy, and carpet of mass m and made of inextensible material is rolled along its length in the form of a cylinder of radius r. So first we are taking this this is a carpet is there, and again its radius is r, and its mass can be taken m, its mass is m, and made of inextensible material is rolled along its length in the form of, we consider that length is taken L. So it is L that is to be taken, and thereafter it is rolled along the length in the form of a cylinder of radius r and is kept on a rough floor. The carpet starts unrolling without slipping on the floor when a negligibly small push is given to it. Calculate the horizontal velocity of that axis of that cylindrical part of the carpet when its radius reduces to r by 2. So this is the initial position. When it is completely a carpet is there of radius r, this is initial position, and when it is being unrolled, now it becomes like this. Its radius is r by 2 only. Its radius is r by 2 only, and corresponding to that r by 2, definitely there will be the change in the mass also. That change in the mass that can be taken as the new mass is the m dash. At this instant, when the radius of that carpet is becoming that r by 2, at that instant what is its velocity? The axis of the horizontal velocity of that axis of the cylinder. So what is its velocity that you have to find? So here first of all you have to obtain that relation between the m and m dash. You have to obtain that relation between that m and m dash. Here the concept is very simple. This problem is also based on the law of conservation of energy. Law of conservation of energy means when this carpet is transformed into this shape, then automatically when into this form, then automatically it is losing its potential energy. At the same time it is gaining its rolling kinetic energy. So that's why the concept is simple, but by application of those values correctly, that is either the m dash like this, application of those values correctly, that is slightly difficult. Now we have to do that. So first of all, m is here and again the m dash. First m can be taken as a density into volume, and it is a rho, and volume can be taken as it is nothing but the cylinder shape. So that's why it is a pi r square L. Pi r square L, that is the volume of that cylinder, pi r square L. So this is m. And in this case, m dash, when you are coming in that second case, rho, the density will not change at all. So pi. Now here the radius is becoming r by 2. So that's why it is r by 2 whole square. And L is here. So that's why it is rho pi r square L by 4. It is nothing but m by 4. So that's why the relation between m dash and the m is, this is m dash is equal to m by 4. That we consider it is first equation. The first equation. And thereafter, when you are coming to this law of conservation of energy, loss of PE is equal to gain of K. Loss of PE is equal to gain of K. Loss of PE means it is coming down from this this position to this one. So that's why mgh is here. So mg, and it is at center of gravity is located here. So that's why mgr minus m dash g, and here it is the r dash. M dash, it will be the new mass. So that's why it is m dash g r dash. R dash, that is nothing but r by 2. R dash is nothing but r by 2. So we apply that r by 2 later. So that's why first we write it is the r dash only. It is a loss of PE. So mgr minus m dash g r dash, because in that problem you are given in the second case the radius is becoming r by 2. So that's why it is m dash g r dash. And gain of Ke means 1 by 2 I omega square is here. 1 by 2 I omega square. As it is a rolling body, that's why it is taken half mv square. Half mv square means it is m dash, because rolling body is this one. So that's why 1 by 2 m dash v square of 1 plus k dash by k square by r square. So that's why it is the k dash by r dash whole square. K dash by r dash whole square. Suppose if at all it is initially in this shape, it becomes a k square by r square.